Now that you've heard a little bit about the three subatomic particles, we will talk about the isotopes, and not the Springfield Isotopes, the famed baseball team on The Simpsons, but instead the isotopes relating to the atoms, specifically the nucleus. Before we talk about isotopes, though, let's address neutrons. And right here, I have before you kind of a rough model that would somewhat resemble the Rutherford model, where you have that dense, positively charged nucleus, and you have the electrons around that on the outside. And if you're looking at this, something should seem wrong. Something does not work with this model. So take a second and try to think about what is wrong. And there's actually a couple things, but we're going to focus on one of them. So hopefully, if you paused and thought about this, you would have known that the nucleus is full of positive charges. And what you know with like magnets, like charges repel each other. And so if you have that dense positively packed nucleus, it's going to repel each other. And those protons are gonna repel, and the atom is going to kind of break down, or we'd say decay. And so to make a stable nucleus, there needs to be neutrons in that nucleus that essentially space out those protons. And so I just threw in green what kind of where the neutrons would go, and they kind of space that out, and they allow that, they diminish the repulsion, so they decrease how much the nucleus is repelling each other, and so the nucleus can be stable. And if I add another one, for instance, that might also work, because I didn't really change it. It still could be stable. Now, if I add way too many neutrons, the ratio's off, and it breaks down, and it decays. And if I don't add enough of them, so like if I only added 4 or 5, it also wouldn't have been spaced out right. So there's a sweet spot. So neutrons represent the subatomic particle that spaces out the positive charges so the nucleus is stable. So to simplify the term isotopes, we can say that an isotope is the same element, so a version of the same element, but with a different mass number. So the mass number is all about that nucleus. It's all about what's inside at that core. And so if they have the same number, so I'm going to write that in, if they have the same number of protons, but the mass is different, what has to change is there's going to be a different number of neutrons. Okay? So an isotope is the same element with a different number of neutrons, maybe one more than another version or one less. And so we'll talk about a couple different examples to try to make this a little bit more clear. So what we have before you are two hydrogen atoms, and you can see the blue represents the positive, and it's in the nucleus. It's at the center. But hydrogen on the left side doesn't have any neutrons, so there's nothing spacing it out. And if you can think about it, does hydrogen really need a neutron? Because there's no two positives repelling each other. Neutrons don't really play a role too much for hydrogen. And so hydrogen can be stable without a neutron. And in fact, the most common form of hydrogen, hydrogen-1, that means hydrogen with a mass of 1, is the most stable one. So here, it has a mass of 1 because there's one proton. Now, on the other side, there is a neutron as well. And so there's two subatomic particles in the middle, and each has a mass of 1. So 1 plus 1 is 2, so this is hydrogen 2, another version of hydrogen. So down below, you have the two ways we do isotope symbols. You can either have like the name, I guess 3 ways, like the name dash the mass, the symbol dash the mass, or you can have that isotope symbol down at the bottom where you have the upper left number is the mass and the lower left number is the number of protons. So it's important to keep in mind that we're always dealing with the same element when we're talking about an isotope, so it's going to have the same number of protons. Hydrogen 1 and hydrogen 2 both have the same number of protons. And electrons aren't going to play a role in isotopes. They'll play a role when we get into ions. So to recap what we just saw in the last slide, there are different versions of hydrogen. And in fact, there's 3 different versions of hydrogen that you talk about. Hydrogen 1, which is this one right here, and this is the most common version. So that's what we're going to see mostly in nature. And since it has hydrogen with a mass of 1, and you know there's 1 proton, it has to have 0 neutrons. But hydrogen 2 has a mass of 2, so it has to have 1 plus 1, so 1 neutron to go along with that 1 proton. And hopefully, if you're following the pattern, you can see hydrogen with a mass of 3 is going to have 2 neutrons. So those are the different versions of hydrogen, and each element on the periodic table has potentially different versions. 1 other version, 2 other versions, 5. Okay, it can have a few different ones, and that's never something you have to memorize, but you can just understand there's different varieties of the same thing. Now, the analogy of an isotope being similar to an M&M's, I think really hits home the point. So what you can see are some of the different varieties of M&Ms, and this is probably not even all of them. And they are different versions of the same thing. They are all still M&Ms. They're all still chocolate candies. But they differ in their mass. So you have crispy M&Ms that are light, and you have peanut butter M&Ms that are heavy. And they differ because they have different insides. They have different cores. So isotopes differ because they have different cores. They don't have different electrons. They don't have different protons, but they have different neutrons. And that's what's different about these isotopes. So I think M&Ms and isotopes do have a lot in common. So here's 3 examples that might help. We have 3 different elements. We have carbon and its common isotopes. We have chlorine and its common isotopes, and silicon. And you can see, you could have 2 or 3, and these are not all of the isotopes of the element. They're just the ones that are most common. You might even find carbon-14 for a little bit, and that plays a specific role in radioactive dating. But what you can see about these isotopes, and I'm going to highlight this column, is, let me use some red, the abundance, okay? So you can notice that abundance is a similar word to like how common they are. So you can see that different isotopes, different versions of the same thing, can be more or less common. So you can see carbon-12, that's the most common carbon isotope. And chlorine-35, that's the most common. And silicon-28, that's the most common. And so when we get into talking about calculating this average atomic mass, which is our next lesson, you're going to see that the average mass is closest to the most common isotope. But that will be a topic of our next lesson. Let's do a practice problem together. So if the question is something like, if lithium has 2 neutrons, what is the mass number? And so there's a couple of vocab words we have to recall. The first thing you want to think about, though, is how many protons does lithium have? And I would never make you memorize that, and I think no chemistry teacher would make you memorize that, because you have this periodic table. So you're going to want to consult your periodic table, and you can find this on Schoology, and you can find this, we have copies, and you could come into, on Wednesday, you could get another copy. But so you're going to want that. So you're going to look at that, and you're going to see, lithium is on the left. It's an alkali metal, and so it's going to have 3 protons because its atomic number is 3. So I'm going to write that 3 down. Okay, so if it has 3 protons plus 2 neutrons, what is its mass number? 5. Okay, so how you would write that is lithium dash 5. Lithium with a mass of 5. And notice how we don't include 3 in that because you really don't need to know lithium has 3 protons because it's already on the periodic table. If you want to write it in the symbol form, you're going to see it most commonly written like this: lithium with a mass of 5. And sometimes you see it, sometimes you don't. I want us to include it. You're going to put the number of protons down there. So this is what I would write for the isotope symbol. You don't have to put a box around it, but I'm just trying to make it clear. So that's the symbol, and here is the naming convention. Both are used just in different scenarios. So we're almost done, but before we go, I would want to say, like, why does this matter? Why talk about isotopes? Isotopes are used in so many different things, and I think carbon dating is one of the methods you might have heard about for isotopes. So we use ratios of the two different isotopes to determine how old something is, and there's cool dating methods, and we don't have time to talk about it now, but if you Google or YouTube carbon dating, I think you'll find some cool stuff. But there are other uses. So the next slide has some more cool uses of isotopes. And I'm not going to go through all of these, but if you notice how many different fields of study use isotopes. Okay, so maybe we're imaging the skeleton, so we're looking at the body, or labeling red blood cells, treating cancer, okay, or looking at the metabolism, or pain relief. Lung ventilation studies. I bet that's going to be really common right now with the COVID affecting the COVID virus affecting the lungs. So there are so many uses, not only in medicine. So most of these are in medicine, but in all fields of science. So isotopes are very important, and so hopefully this base level of understanding can help you as you continue studying different fields of science.